Hello, thanks for joining me today. It's my pleasure to be here, and I want to thank the Quantum AI Institute for inviting me to be part of this AI Quantum Sustainability Summit on Science, Technology, and Innovation. Today, I'm going to be talking to you about optimizing the planet with quantum computing. My name is Murray Tom, and I'm the Vice President of Quantum Business Innovation at D-Wave Systems. My primary role is to help our customers build business value using quantum computing technology. And I've had the great pleasure of working with D-Wave for a little over 20 years. Okay, let's get started. So a little bit of background. I work with D-Wave Quantum Incorporated. We're a company with a little over 200 employees, and we're a full stack quantum computing provider. We work with a variety of customers around the world, including many whose names you might recognize, like MasterCard, Johnson & Johnson, Denso auto parts manufacturer, and a variety of others. We have a technology platform which includes the development of quantum computing platforms themselves, the hardware, the computers, as well as a cloud service platform that provides you with real-time access to those quantum computers so that you can start using them for business applications and to impact the kinds of important applications that are challenging us around the world today. We've got a really easy-to-use Ocean software development kit, which allows Python programmers to begin building their applications and leveraging quantum computing technology. And we also have a launch program for helping you accelerate you along your journey from discovering those problems which are well suited to quantum computing all the way to full production deployment. Okay, so let's begin at the beginning, and I'll just ask you to focus not so much on what's on the slide, but what I'm saying. The most important question for us to consider here as a beginning point is, what are we talking about? What is a quantum computer? So fortunately, there's actually a very simple way to think about this. A quantum computer is just a device that's going to allow us to use quantum effects to accelerate calculations. That's all that it is. Once we've had the idea of building a computer that has that capability, it turns out there's actually a variety of different models or ways that we can use quantum effects to act as a resource for our computers to help us with that, accelerating those calculations. And at D-Wave, we're building two of the primary approaches of quantum computing. And they take their names from the fields which sort of inspired those ideas. So some of the ideas about how to leverage quantum effects for our calculations came out of the computer science community and the information processing community, having to do with the inspiration from the classical computers we use, which involve logic gates and logic gate circuits, and it's often referred to as the gate model of quantum computing. Another community references it sort of comes out of the optimization community, which is looking at solving optimization problems, and they also took inspiration from physical processes that are used in like metallurgy. So thermal annealing, like we use when we're processing metals, inspired simulated annealing in the field of optimization, and that's where annealing quantum computing emerged from. Now, the reason why I'm mentioning that there are multiple models is because the differences in the models determines the rate with which they're maturing, and also which applications they're going to be suitable for. So which applications are going to see acceleration from quantum computers in the near term and then in the long term. So as we're looking for changes and the ability to solve important and challenging problems, we need to have an idea of which ones are we going to be realizing immediately and which ones are we going to be realizing in the longer term. So in the case of gate model quantum computing, the really attractive applications there are when we need to simulate the electrons around molecules, the kinds of tasks we might see with like molecular design and drug discovery, development, as well as solving, let's say, like differential equations, the kinds that are used for fluid flow calculations, like fluids over cars, and in 3 dimensions. That's what they're going to be best suited for. And those models of quantum computers are maturing a little bit more slowly. Those types of applications are probably not going to see acceleration in a commercialized context for 7 or more years from now. Part of the reason why it's maturing more slowly is because of the way that quantum effects are being leveraged there as a resource for the computer. It's allowing those computers to store more information, and they're storing the information in the quantum states. you may know this, but you may not have heard this before, but quantum states are famous for being delicate. They can collapse. And if you're storing information in the quantum states, when they collapse, the information that you stored there is lost. So it requires sophisticated techniques for error correction, and that's actually going to help us unlock the value in some of these really critical applications. Now let's consider annealing. In annealing, this is going to be really relevant to applications that involve combinatorial optimization. So if you don't recognize that term, it occurs all over the place in applications like employee scheduling, autonomous vehicle routing. It can also be involved in like fraud detection, patient trial optimization, and it has a lot to do with resource allocation and transportation types of problems, which I'm going to be talking about today. What's great is that technology is actually realized. And at D-Wave, we have the world's largest, most highly connected quantum processors, our annealing quantum computers that are available in the cloud for you to use right now. And they are currently supporting our customers' real-world application use cases. So it gives us the opportunity to impact applications right now with quantum computers. So how should we think about the value of quantum? Well, there are going to be a set of use cases I'm going to talk to you about because it is absolutely the case that we have the opportunity to bring value to businesses and to our operations around the world that are going to allow us to run more effectively, more efficiently, or to respond more quickly to change. And a lot of these are going to help us solve current problems faster or better, either by reducing costs, increasing revenue, or allowing us to use our resources more efficiently, which is going to be really important from the perspective of impacting sustainability. But we also have to keep in mind that there's enormous potential with quantum computing. There are a number of application problems like the ones that I discussed with you, where people are expecting a tremendous impact from quantum computing technology. And one example of those would be in the area of quantum material simulation. So let me give you an example of that. At D-Wave, we have developed 5 generations of quantum processors. And our early commercial quantum processors struggled at tasks associated with quantum material simulation. In many cases, we couldn't actually produce answers that would be usable in that context. We went that way, and then we emerged from that. In 2 product generations later, we were able to tackle some quantum material simulation problems and be 3 million times faster than classical computing. That is an unbelievably fast pace of acceleration. And that's the kind of development in quantum computing that has got us a lot of us very excited about in terms of being able to leverage that new resource, that new ability to perform calculations that were previously inaccessible so that we can try to bring about this unimaginable social and economic impact, and particularly to impact some of those most challenging problems facing society today, like the subject of our discourse, which is sustainability. And, as we're meeting with business leaders and CIOs and folks who are trying to tackle some of these challenging problems, when they're observing this very rapid change in the development and making problems that were previously very difficult to solve suddenly much more accessible with quantum computing, it's starting to become really important and apparent to them that they need to discover the places where quantum computing is going to provide relevance. So let's start talking about use cases and how we can leverage quantum computers to solve real world problems. And I'm going to begin here by showing that this is a trend that has already sort of reached our awareness. There are 39% of companies that are experimenting with quantum computing today. The market research is in here, and the areas where this can provide impact are expected to have, an $850 billion impact by 2040. It might surprise you to find out that there's over 99 near-term commercial use cases that have been identified for quantum computing. And what it also might surprise you is that they're already being used to support production applications today. So when we talk about use cases, I'm going to focus the discussion today on those use cases that are really going to impact sustainability. Let's take some inspiration here from the field that have sort of directed us towards tasks and challenges facing us with regards to power optimization and energy reduction. And then in a second category, optimizing our transportation networks, improving our scheduling and our distribution efficiency, as well as discovering new materials and chemical simulation in order to be able to bring about some transformative change. So, it's absolutely the case. We all have to realize that this is about our energy use globally. And the scale at which we're consuming energy is enormous. And it's a very large group of us, right? It's the whole planet that we're trying to help to impact. So it's going to take us a while to develop that. As we're doing that, there are a number of areas that we can begin to realize change immediately. Amongst all the ways we're using energy, let's use it more efficiently. Let's, reduce or take that huge volume and reduce the energy consumption for the tasks that we're currently doing. That's an immediate way for us to realize impact from a sustainability point of view. Let's absolutely take a look at new technologies that enable us to change the way we're doing things. And let's also pursue some of that cutting edge research about discovering new materials that allow us to solve problems and distribute and store energy in ways that we haven't been able to discover yet. And it's those first and third examples which I'm going to focus on in terms of near-term applications for quantum computing. All right, so let's talk about a real-world example. Savantex is a software company that built a solution for the Port of Los Angeles to allow them to operate their port, Port 300, more efficiently. When they looked at those operations, what they found was that these large cranes, these yellow cranes, they're called rubber-tired gantries. It's the amount of time that they spend moving materials and the amount of time they spend moving when they're not actually picking up containers determines the efficiency of the overall port operations. And they were able to build a quantum hybrid solution that allowed that port to increase the amount of cargo that they were handling by 60% each day. So let's think about this from the perspective of we have a global footprint, and that footprint, like the port, determines our ability to move materials in a given area. If being able to move more in less area means we don't have to broaden that footprint and expand into more space. We can accomplish the tasks we need to do in the areas that we have available to us. And what's great about this is that in addition to seeing this increasing the amount of cargo they were handling for their given operational port area, they also managed to reduce the truck turnaround time by 12%. Let's take a look at another example here, this one by Mitsubishi Estate and GrooveKnots, which was looking at specifically helping cities to become more sustainable and looking at regular tasks like waste collection optimization in order to reduce distance traveled, number of trucks required, and the CO2 emissions. Here, they were able to accomplish a study for a citywide plan that was able to reduce the number of vehicles needed for the waste collection by 59% and reduce the expected CO2 emissions by 57%. So, absolutely a scenario where by looking at the way we're operating and using, quantum and classical technologies together in a quantum hybrid manner, we can actually bring about changes that can be realized very quickly in order to use our resources more efficiently. E.ON is a global power provider that is been investigating quantum computing to look at the energy grid of the future. So certainly, we're seeing a major transformation from an era where electrical grid transmission was a hub and spoke model, a very large plant that was generating all the electricity and then just distributing out to a community network out from it. And we're transforming into a much more complicated network where many different areas of the network may either be generating or using electricity or storing electricity. And that makes the real-time operation of those grids much, much more complicated. If we want to be able to realize the increased efficiency that these sort of mixed mechanisms for generating electricity, storing electricity, and using electricity enable for us, we're going to need to be able to run optimizations quickly. And E.ON actually did a study on some test use cases here where they were able to accomplish some tasks to do with planning and operations of electrical grids and reduce the time for computation by 600 times. So, really an enabling capability in terms of like real-time planning for the operations of the electrical grid. Now, I mentioned earlier in the talk about some quantum material simulations that we had done at D-Wave, where in 2 product generations, we went from not being able to really resolve the problems to being 3 million times faster. So since that time, we've actually been able to further those studies in quantum material simulation and also innovate in the way our quantum processors are performing those calculations. And particularly, we're able to take our commercial quantum processors and operate them in a mode called coherent quantum annealing. So quantum annealing is the type of quantum computer, and coherence means an ability to operate it without it interacting with the outside world. And when I say not interacting with the outside world, I mean not even a single photon is actually interacting with the circuitry and interacting with it and causing a disruption. Being able to operate in this mode, we have been able to demonstrate in this Nature publication that we can improve solution quality faster than classical computers can for these very difficult optimization problems. And we've been able to do this demonstration with both theoretical results showing that classical and quantum computers actually perform differently at improving solution quality, as well as experimental measurements on our commercial processors, our full-scale 5,000 qubit quantum processors that actually fit those results. So it's a very exciting time in terms of looking at, revolutionizing the way that we're looking at material design and simulation, making use of these new, fundamentally new capabilities. Okay, so that was a quick tour of a set of use cases. And part of the reason why we really wanted to cover that at the beginning is because when I'm speaking with developers, many of them say, I'd be more interested to learn about quantum computing if I knew what I could use quantum computers for. So now that we've had a chance to look at what we are going to be able to use quantum computers for, this is how D-Wave is basically enabling that technology. And it's these 4 elements. So we are actually, building the quantum computers themselves. And we have, as I mentioned earlier, developed and deployed 5 generations of commercial quantum processors. And the latest one, our Advantage quantum computer, has 5,000 qubits, 15-way interconnectivity. And as I mentioned earlier, it's the largest, most highly connected quantum processor on the planet. And we all have access to it. It's actually available online through our Leap Cloud platform to 39 countries around the world. That Leap Cloud service allows developers and users to actually interact with those quantum computers in real time. So you can actually submit problems to those systems and get answers back in seconds. And we have developed mechanisms to make that application development really easy, as well as maintaining those systems on multiple quantum computers around the world with better than 99% availability. And we have quantum computers here in Burnaby, Canada, where I'm located, as well as at the Information Sciences Institute at the University of Southern California in Los Angeles, and as well at the Jülich Supercomputing Center in Germany. Now, when it comes to actually developing applications, we have open source software development kits available in Python that people can use in online IDEs or in local downloads as they're building their applications. The great thing about having an open source stack is that you can begin by focusing on application development, but the further you go, you can dive in and learn more about the quantum computing technology and how those systems are working. All those layers are available to you in the open source stack. From onboarding applications, it makes information technology teams, makes their task easy for scanning over new application code and making sure that it's secure and it's going to function well for them. And it's also important for engaging a broad community. The quantum computing industry is engaging folks at many different levels. There are physicists who are working very closely with the core machine instructions of the quantum computers. There are mathematicians who are developing techniques that allow us to build abstraction layers in the technology stack. And then there are application software developers who are building on top of the stack in order to impact these real-world use cases for us. And what's great is that these communities can come into this open source stack at many different layers, and all of the work that they're doing is creating a compounding benefit for these applications that could impact sustainability today and in the future. We also provide a launch service at D-Wave to help accelerate folks along their journey from problem discovery to building a proof of concept that allows them to see in real world use cases that they can actually generate value with our quantum computing technology. get into limited production scale releases, and then transition up to full scale production releases. And an important element that I want to highlight is that we have determined now, with all this work we've done in this technology development, how to get quantum computers and classical computers to work effectively together. When computers are tackling these challenging optimization problems for us, it's a little bit like they're moving through a landscape of solutions, and they're searching through that solution space to try to find the best solution. Classical computers are very, very good at looking near a position. So they find a solution and they look just around it and they find the next best, and they keep moving. It's like a downhill run. So much so that if the landscape happens to be shaped like a bowl, there's no way to optimize that problem better than a classical computer can do. But a lot of our industrial problems that we're facing, and the ones that are challenging us in sustainability, are not shaped like bowls. They're actually have a variety of shapes with lots of roughness, a little bit more like finding the lowest point in the Sahara Desert, except that it's much, much larger scale. There's many times there are more possible solutions we could be looking through than there are estimated number of particles in the universe. So, to face that challenge, we've actually determined that those are complementary capabilities between quantum computers and classical computers, and we can bring them together to create hybrid solutions and really enable this powerful technology and make it very easy to use. This is allowing us to build our binary quadratic model solvers and our constrained quadratic model solvers, which allow you to tackle problems of up to 1 million variables for industrial scale, up to 100,000 constraints, and to give you a very powerful way of representing your problems to make application development easy and accessible to even small teams of developers with just 2 or 3 folks working on it, so that in a period of weeks, they can actually begin to see the value that they can generate with the technology. And in a small number of months, they can actually get an application built and developed and deployed. Okay, so I'm going to switch my screen over and actually provide a live on my end, pre-recorded on your end, demonstration. So if you want to get access to D-Wave quantum computers, it's just as simple as typing in D-Wave Leap into your favorite search engine, and any of the top links will take you to our platform. Once you've signed up and logged in, then this is the screen that you'll see. I've already logged into my system, and you'll see a dashboard which shows you how you can interact with our demos, start exploring examples and a variety of our other resources. You'll get immediate access to the quantum computing systems to submit problems. And if you want to open source the software development project you're working on, you can actually link that to your account, and we'll renew your access every month. What we have found is that it's not all that common for folks who are building applications today to go through 4-year computer engineering degrees. It's much more common for folks to actually take sort of compressed boot camps, learn the skills for programming, and then actually go out in industry and start working on problems and learn on the job, sort of a professional training. And so what we've done to help enable folks who are going through that path is to actually build code examples and Jupyter notebooks that actually demonstrate how to tackle problems so that you're not starting from a blank page. You can actually begin from an open source example that demonstrates how to map tour planning, bin packing, or nurse scheduling to a problem. So this allows you to actually, in this case, looking at bin packing here, explore the example and how to run it. And if you have a GitHub account, right, even if you don't have a GitHub account, you can view the code on GitHub. But if you do have one, you can also open it in a CodeSpaces developer environment right in your browser using VS Code. Now, for this demonstration, that's exactly what I've done. So I'm going to switch tabs here in my CodeSpaces stuff. I'll restart my CodeSpace as we're talking. So this is actually going to deploy a computer in the cloud and allow us to actually run a web application. And this is going to be a little bit like, what's the word I'm going to use here? This is actually like the development operations process of like building and deploying a web application in a mini version here live on your screen. So in this case, we have actually opened the code here in this development environment. And then from here, we can actually start it up. Once we do this, this is actually going to turn this developer environment into a mini server using some temporary resources that in an industrial application would be deployed on permanent resources. It's going to run this application code, and then it's going to open a port that's going to actually allow me to deploy a web application in this new browser tab, which is going to call back to that server. So this is really like, once your process is built and you've developed a quantum hybrid application, this is sort of what the end of that process looks like, and what your teams would be running to execute this. So we worked with some businesses who were looking to improve their bin packing. So they were packing pallets and looking to ship them, and inefficient bin packing means that they need more pallets. It takes up more space in their trucks. And in many cases, that means they're having to send more trucks in order to execute on the delivery. So being able to tackle bin packing more effectively can really have an impact here from a transportation sustainability point of view. But the key thing is that when you're using mixed containers of different sizes, this is actually known to be one of the hardest problems to solve at scale. I'm just going to solve a small version of this, and I'm going to give it a 10-second limit. I'm going to ask it to pack in a single bin 15 different cases. Now, ordinarily, if I were a business, I would have a set of cases that I need to pack in, but I'm going to actually generate that input data and say that the cases are between 1 foot and 5 feet in dimension. And I'm going to put this into a standard shipping container that is 20 feet long, 8 feet wide, and 8 feet high. Okay, so this is our application. When I click run here, we are actually now submitting this task to an API. We're deploying computers in the cloud, which are ingesting this whole large problem, beginning to work across it, breaking pieces out for the quantum computer, and the quantum computer is suggesting moves through the solution space. So those quantum and classical resources are working productively together in a complementary way to generate a solution. And in just a few moments here, given that 10-second limit, we should actually get a return from those quantum hybrid resources that allows us to consider a solution. And there it is. Okay, so here we are with a set of those cases that have been packed within a bin. Okay, so that's as easy as it is. We have now fully on screen deployed a web application and submitted a problem to a quantum hybrid solver, and all of that technology stack has been working for us with just the click of a few buttons. Now, we also have enabled in this demo the ability to check out this CBC Python mixed integer programming solver. This is a classical only solver for tackling this, and it's absolutely production quality. It's used in Google OR tools and other methods. So let's submit the same problem. And in this 10 seconds of time, for a problem of this scale, we're going to be able to see a solution here. So let's check what we see from using this classical solution. So there we are. So we've got our plan here using that classical only solution. So now what I'm going to do is I'm actually going to change the problem. We've got a business. Let's imagine we've got a business. We're solving problems here, and the business is growing or evolving. So now we're going to increase the number of containers we need to ship from 15 to 17. And I'm going to submit this problem again to this classical solution. It has to work from scratch. Now, with classical computers, you would think, oh, 2 problems of comparable size, they must be of near comparable complexity. But as a matter of fact, I mentioned earlier that bin packing is one of the hardest problems. The difference in complexity of 2 problems, even of very close size, can be radically different. So in fact, here, this classical algorithm is now struggling just to get the cases in the bin initially. 10 seconds has now become not enough time for it to solve this problem. That's only 17 cases instead of 15. This is exactly the experience of businesses who are dealing with resource allocation, scheduling, transportation logistics and last mile delivery, and bin packing, just like this example. So let's go back over here and switch back over to the quantum hybrid solver and ask it to use that same 10 seconds to solve this 17 case problem. What we're learning is that, our, industry and our colleagues who are tackling these really challenging problems that are, really related to sustainability, they're dealing with a lot of complexity, and we need to provide them with the tools to be able to push the bounds and use our resources more efficiently today so that we can build off of that and help achieve our sustainability goals across a variety of industries. All right, so now we have our solution. from our quantum processor here for the 17K solution. And you can see that it managed to actually get the boxes much more packed down in that bin. So let me switch back over here to finish my presentation. As we're working on these problems and looking to incorporate these new technologies to bring these transformative solutions, there's a common journey that we can kind of articulate in people's experience. The first one is, let's begin to identify use cases. What kind of problems are you struggling with? What are the areas of your business where it seems difficult to sort of make an impact, or you're applying more computing to it, but the solution doesn't seem to be getting much better? Let's start exploring how quantum computing can begin driving towards the results that you want to achieve. And then as a second step, that involves really clearly identifying what those problems are, and then creating a formulation that quantum computers can provide. And also, as we're looking at those problems, making sure that we segment which ones lend themselves well to quantum computing, because the nature of what's making them challenging is complexity, and which ones should be shuttled off to different resources. Third thing is that it's important to make sure that we have the data available for the problems to be solved. So this is really about, taking descriptions of, I want to minimize the average height of cases in a bin, but I also want to make sure to constrain them so they only rotate in 90-degree increments. That's the description of a problem that then, given business data of like, okay, well, which cases are you looking to pack and what's the size of the container you need to pack them in? That's the data you need in order to be able to make a full formulation that can generate an output and a plan that you can work with. And lastly, implementation. So once we know the problem and we have the data, then it's putting this together in software and tuning it for performance in order to be able to make it work in the application workflow that's important to your business. And we have teams and tools that can help you along that path. So to get started on your quantum journey, have a look at this list of applications that we have available online, an expanded list from just the use cases and real-world applications that I discussed. Certainly sign up for LEAP and get access to it and begin interacting with the systems right now. We have a training program that you can find and learn how to formulate problems for these systems, and contact us to get started. So thank you very much for joining me today. It was my pleasure to share this information about quantum computing and some of the exciting use cases. I'm really looking forward to working with all of you and making an impact on sustainability today and in the future. With that, take care.